All right, welcome everyone to the Server Engineering Workshop room. Up next I'm John Stewie, I'm co-lead for the server project. CMAC was on the stage before, looks like he stepped out of the room after he got off the stage. Up next on the agenda we have Greg Casey doing the Gen Z technology enabling. Greg?
Good afternoon, everyone. Please, if you have some questions, please raise your hand and we'll address them immediately. I think most people are familiar with Gen Z. It was a consortium that was launched in 2016. It's an interface for pooling memories. We've had several demonstrations at several of the big shows to demonstrate the protocol, talking to these memory pools. We've released IP. We have silicon vendors working on detailed silicon. And we've released the draft of the Gen Z documentation is available for public review. We're about 64 companies right now in the consortium. All the major players are part of it. This is a list of all of them. I work for Dell, and my boss is the president of Gen Z. And so what problem are we trying to address? The problem we're trying to address is the bandwidth problem going in and out of memory, the number of pins going in and out of the processors. And over the years, we've gotten more and more cores inside these processors, and we've kept the pins more or less constant. The number of DDR channels are going up, so our pins become a problem. But more interesting, if we look at the right-hand side of this graph, you'll see that our bandwidth per CPU or per core is actually going down. And that's a problem, so we're trying to think of ways, the specification tries to figure out ways to get more bandwidth in and out of our cores without adding pins. And the real estate problem of putting that many DIMMs that close is also a problem. So what we're doing is being able to take those memory resources and move them remotely. It's a layer architecture. We have groups within Gen Z that talk about the physical. The previous presentation, they were talking about the connectors. We have a discussion about the connectors. The 4C connector came from the work we did. Additionally, we have PCIe kind of interfaces to it. And so if you think of the layered architecture, we have the different resources that can play into this infrastructure and talk to one another. It's a packetized transport, so all the communication, where you're thinking of DDR, for example, it's address data. So this is a fully packetized communication, which means we can go through switches. It's scalable, it's proportional power, the proportional link, physical link. What we're saying there is that it's variable in width, just like PCIe is, but it's also not necessarily symmetric. One can put out 2 lanes or come back with 6 lanes or that kind of thing. So you can dynamically change that. The comment about breaking the processor memory deadlock is we go and develop a new server and a new processor and new memory. Up to this date, we really had to wait for the memory technology to be available from the processor. It'd have to be verified. So we wanted to have a universal bus that we could introduce new technology and break that development cycle so we could start bringing in new technology as soon as it's available. We also have constructs in the protocol for doing accelerators and smart memory modules. The solution is an evolving path for doing memory semantics across the interface and cache coherency event in the next generations. We have the ability to do unmodified OSs, and using the MMU. So it's directly, as opposed to PCIe, which is on the I/O side, Gen Z is on the memory side, and so when you get a cache line miss, the architecture is to go out and effectively get that memory semantic data from the memory. It's market-driven packaging and topologies. We've talked about the different multiple links. It's a switch topology. We have both. So it comes in three separate entities: the host side, the fabric, and the target. So this is talking about the switch side, where we can have switch topologies. So topology is arbitrary. PCIe typically is a tree structure. Gen Z allows for arbitrary topologies. We have different mechanical form factor groups. We've defined a set of mechanical form factors, and we can either support the PCIe legacy kind of form factors or some more innovative module types. We talked earlier about the new scalable connectors, and that's what several other people have talked about, the Gen Z 4C connector. That came out of this group, and it's been adopted by OCP. The datagrams, the requesters ensure the reliability of the transport. Responders simply execute the request and generate the response if required. To verbalize what that's happening, a CPU needs some memory. It encapsulates that request in a packet, ships it across a switchable fabric. The responder then unfolds it, looks at the request, responds with a response packet with the correct data. I said earlier the datagrams can operate from a point-to-point operation or in a switch topology. Multipath is an option in that structure, so it can, for bandwidth reasons or for fault-tolerant reasons, it can choose different paths. There's also strong ordering concepts if you need to have those, and different encapsulations are anticipated. So I talked around this a little bit, but let's look at it in a diagram. In this diagram I have on the left-hand side, I got a processor and its media memory module. And basically right today, we have a media controller that sits in the processor, and it generates a DDR bus communication out to those DRAMs. The vision that Gen Z has is we actually move that media controller, that memory controller, out to the DRAM module. And we communicate it to it over some universal Gen Z communication path. Therefore, we've decoupled or split that transaction, so all of a sudden we can have new memory technologies or new processor technologies come in and take advantage of it. It's high performance. We've been demonstrating stuff at 16 gig. We have two kinds of PHYs that we're talking about, PCIe-based PHYs and 802.3.PHYs. Our PHY group is specifying all the way up to 112 gig transfers at PAM4. It's reliable. There's no stranded resources. And what we talk about stranded resources is, as a server design company, we have our biggest products are two socket servers, and we have a lot of memory stuck behind those two sockets. And customers have a lot of investment in that, and if there's some way to liberate that and bring it out on the other side of the processor and have it as a shared resource among multiple processors, or have those same processors talk among themselves, that's kind of where Gen Z is. Secure, there's different keys. There's our next specifications talking about encryption. Flexible, like I said earlier, multiple topologies are supported. We believe it'll lower our CapEx and OpEx costs as we go forward. The diagram on the right kind of shows a conceptual model of what this environment might be. I show several SoCs, systems on a chip, GPUs associated with those, talking across a common Gen Z fabric which has some DRAM modules, storage class memory modules, and even encapsulate going out to network or storage resources. We go a little bit further into the architecture. The top is kind of reminiscent of our current situation where we have PCI buses coming off our processor to the left, the standard PCI add-in boards. Off to the right, we have DDR modules using standard DIMM modules going off to the right. In this picture, we draw our vision of what Gen Z, where it would intercept at first. Probably at first with a bridge option where we're taking some high-performance CPU bus and bridging to Gen Z. One can read in that AMD high-performance buses or Intel or Power or ARM. Then Gen Z, it comes out of that, and we go into a fabric where we can see all these additional resources that we talked about on the previous slide. The overall reason we're trying to do this is to break out and disaggregate our servers. Up to this point, we've been at Dell, we've had many different attempts at disaggregation, but there's one area we've never been able to break apart, and it's the CPU and the memory. We do it through software schemes inside the server, but still you physically really cannot reallocate that memory conveniently with high performance capabilities. So what this does is we allow the memory to be totally disaggregated where it can be associated with any CPU or any memory other processing unit, be it a GPU, an FPGA, or a processor. We talked earlier, we had a work group that is in the connector definition. We, about 2 years ago, had an evaluation of connectors, and we came up with what we call the Gen Z connectors. Since it's been donated to SFF, and other people have taken advantage of it, one of which is OCP, which we appreciate. It's very high fidelity. We believe we've had demonstrations of it at 112 PAM4. Additional work is going on with sidecar modules that fit on it that are optical. And of course, I show both vertical and right angle. And it's supported by multiple vendors. We talked earlier about different form factors. We have a form factor group that's looking at what conceptually this disaggregated server might be. And so we've looked at what the optimum sizes might be for that we would anticipate. So we have a variety of sizes that we start anticipating what these Gen Z modules would look like a couple years out. And I've illustrated several of these here. They can support 1C, 2C, and 4C connectors. And the people that aren't familiar with the Gen Z connector, the C is for chiclet, but it's 4 bits wide. And so each, a 1C connector is 4, 2C is 8, and a 4C is 16. What's Gen Z done since last year? We'll give ourselves a scorecard. We've gotten out our core specification, 1.0 was released in February. We have a 5 spec, which has been released. It includes 25G NRZ, and it also accepts the speeds associated with PCIe Gen 4 and Gen 5, which is 16 and 32 gig. I talked earlier about the scalable connector specification, and we've had internal adds, internal cabling inside of a server has been defined, 48-volt power delivery in the connector space. And that leads us right into what we call the 4C high power version. As I said earlier, we donated to SFF, and that's, no, excuse me, I misspoke. The 8639 are the disk form factors, 2.5-inch disk drive, and the scalable form factor 8201 is the 3-inch form factor, and these are some of the form factor work that we're doing within the Gen Z consortium. We have a company We have what we call ZFF, Scalable Form Factor, which is a document which we've, and it's at 1.0 and it's been shipped out. We also developed a specification called PEC-FF. So it's PCI equivalent form factor, which we use the Gen Z connector on. It's essentially the same size as PCIe, but it gives us better fidelity at the speeds we're talking about because of the newer connector. It also delivers by 32 into it, so if you really wanted to get aggressive, and it also has across-the-top cabling for GPU applications. And we're working right now heavily on management software, test, and other design guides. My call for action is we appreciate everyone that's already engaged with Gen Z, but we always have room for more. We only have 64 companies, and we have room for more. We believe Gen Z is open, and our bylaws are it's an open community. We've shared the and to emphasize that, we have shared our Gen Z connector to the industry. We embrace the EDSFF effort, and all of our release specifications are public and are on our website, which is listed below. Gen Z allows all the companies to focus on innovation areas of their expertise and provide interconnect for all these innovative products. So if you're designing a GPU or designing a CPU or designing memory or designing whatever your application is, we embrace that, and that's what Gen Z's focus is that interconnect going into the future. A lot of discussion in the press in the last week about something that Intel did. Intel came out with something they call CXL. Gen Z embraces that. We're pleased to see that. And we feel that that'll give us high performance capabilities directly out of x86 processors from Intel. How can OCP and Gen Z cooperate? Well, a lot of the employees, I know inside Dell we have a lot of participants in OCP as well. And so we cooperate in that way. But in a more formal way, we really need to look at how the evolution of server design can be brought together, and when we disaggregate the memory, how we can use these common buses, Gen Z, OCP, and CXL into the future, how those can come into play. I think that's the end of my presentation. Questions from anybody? Yes?
I saw in the 1.0 spec that you were supporting 32 gig NRZ.
Yes.
Are you, or do you have plans to move up to 112 or 50?
Not at NRZ, no.
Not NRZ,
no.
but
PAM4, PAM4,
yes.
yeah.
Okay.
It is in our PHY spec, and so no one's actually executed on it. A lot of the silicon people are actually looking at that as to minimize the ball count and to go to the higher signaling rate.
Okay, and my next question is, are there any, so I'm with a small startup, and so one of the things that limits us from sort of looking at Gen Z seriously is it seems that I haven't seen any products announced or any word on the street that people are working on, actual silicon for this, and so it ends up being a chicken and egg problem.
It is the chicken and egg problem, and I know some things I can't say, but there are people that are either fully committed or really thinking hard about silicon products. And so as a Dell and as other OEM kind of manufacturers, we're kind of stuck. We cannot offer cost-effective products without that enabling silicon. And so we're kind of waiting for that to happen, and the design cycle for that enabling silicon is 1 to 2 years. So we anticipate that's the time window we're talking about.
Okay, so
I agree with your observation.
So without naming names or naming products or anything, are you aware of any company that's got silicon in the works for Gen Z products?
I'm aware of companies that have silicon in the works.
Okay.
But I can't name those companies.
I understand. Can you say anything about whether there's a switch coming down the road?
there has to be a switch.
That's to me key, so that's
Yeah,
what I was wondering.
Yeah, the switch is key. It's a packet-based switch. It's a fairly large radix to get the kinds of things we want to deal with. From an intellectual property standpoint, we've demonstrated on FPGA a lot of our switch functionality at Supercomputer and Flash Memory Summit. The FPGA company has been very helpful in allowing us to drive that technology in those platforms. So they are still probably a little pricey for mass production. Our FPGA people probably argue with me with that, but I think,
Right.
So we're definitely ironing out the kinds of details we need to do before we go to hard silicon.
Okay.
Yep. Any other questions?
Yes.
Yes.
With Intel, not on board, obviously, how could this standard be successful? I mean, because really for Gen Z to be successful, you want to have the most efficient interconnection possible.
Oh, absolutely. Latency and bandwidth are key.
And their inherent interest is not to make, I think for Intel, not to make Gen Z successful, I think.
I don't know about that. That's way above my pay grade.
Yeah.
But nonetheless, I think we're excited about the CXL announcement this week. And we think that would allow us to make effective bridges.
But again, it would be another bridge, They're just trying to, they want to keep control of this, and I don't think they want to hand it to you. So I think it's a very difficult spot.
I think you should just hang on. I think, I think that they have the same laws of physics apply to them as well.
But they want to expand their ecosystem. They don't want to give the control to you, I have one more question.
Yes.
So as you go from 25G NRZ to some of the higher speed PAM, you're going to need to have FEC, and the FEC potentially could add 150 nanoseconds or so to the links. Could that be an issue for your application, or you don't care about that sort of latency?
We do care about latency, and we would never embrace a FEC that applied 150 nanoseconds onto the path.
Yeah.
There are lighter versions that would allow something significantly lower than that.
But it wouldn't be significantly, but I mean, you could cut it by half, but
that's significant, 150.
Right, but like what kind of latency can you tolerate?
The goals from a design is to keep those links between 500 and 1 microsecond.
Well, we were talking about 5 microseconds?
No, nanoseconds, excuse me.
Can you say that again?
Yeah, with somewhere in the range of 500 nanoseconds to 1 microsecond.
Okay, so that's what I mentioned earlier was 150 nanoseconds.
Yeah.
So that's,
but you're just saying the addition of FEC itself.
The addition of FEC would be 150.
That's too much.
That's too much,
Yeah.
And you want that to be less.
Yes.
Okay.
Yeah.
So when you talk about 500 to microseconds, you're
Yep.
talking at
End to end.
application level,
End
to end.
Yeah.
Thank you.
Yep. Yes.
Ali asked the same question.
Okay. Very good.
I also had the latency question, but the second question is about energy. So when I've directly coupled DRAM, right, like DDR 2400 or whatever, versus running all the data traffic through these power burning 56 or 112 transceivers.
It's a good question. It's a good question. We have customers that want so much memory it's just physically impossible to put it close to the processor. So then you also have the cost of those memory resources. How do you share those? So then you get into the economics of that. You're absolutely right that you're going to ship data from here to there. You're going to burn power to do it.
Do you anticipate systems then that have both directly coupled?
Absolutely, absolutely. That's what my diagram showed. I would say that we would have a certain set of DRAM DIMMs as we traditionally do, but our software eventually has to get smart to say, this is the area that needs high performance memory, this is the area that takes a little bit slower memory, and this is the stuff that has to have persistent memory. So we have to color our memory requirements in our applications different. So there's a lot of work on how we do that. And then the adding and subtracting of memories, one can envision these modules of pulling out of memory. I would not suggest going out to your server and pulling out a DIMM right now, because it will blue screen on you immediately. But we anticipate that this kind of technology is something we want to do. How we do it is still TBD. Any other questions? Yes. I'm supposed to be in the middle of the camera.
So I can see, you know, based upon your diagram that having a centralized memory pool of whether it's persistent memory or slightly slower than main memory.
Yep.
But one of the things that, you know, seems attractive about that is then you can partition that memory up amongst clients, sort of in a, you know, in a hyperscale center. But that would require some management techniques and that sort of thing. Are you guys?
Those are good questions. The management is a whole work group we have right now. The additional thing is security of those things. So there we have both area keys and what you call area keys and region keys, or access keys, excuse me, access keys. So each contributor has access to a certain memory, and there's keys that allow it to get in and out. There's also region keys, which are by address ranges. So those are two security things. Once you start allowing different CPUs or different resources to come in, then you have to worry about, you know, malicious or accidental stomping on other people's resources. So that's totally being anticipated.
Okay, and how far along are those additional aspects of the spec? Are they already completely
The spec,
done?
they're all in there. Yep.
And so the management software piece where the allocation and...
The discovery and the allocation is still under work right now.
Okay,
Yep.
okay.
The base specification has all the constructs to make it happen, but the coordination of those constructs is still being developed.
Okay. Now, if a small startup wanted to join the effort to help define some of these things, what would the cost typically be to join your effort?
Oh, I think it's $4,000 per year, maybe 10. If you're a government agency, I think, or a university, you can get for free as a non-voting member, but I think a corporate is in the 5,000 to 10,000, I think, but I don't know.
Okay.
Send me an email, I'll find out for you.
Okay, thank you.
Yes.
You know, the industry's been hit with a bunch of side channel security attacks, and this kind of technology, you know, is potentially vulnerable to side channel attacks, since there's so much shared stuff going on. Is there any efforts in that world?
I talked about the access and
But also just the usage too. It's not just access; it's people observing the usage
yeah,
as it goes by.
I guess I'm going to have to beg that I don't know. Yeah, that's not my area of expertise. Okay. Sure. Yep. Anyone else? Well, thank you very much. I appreciate it.
Yeah, thank you, Greg.